Welcome. In the next hour and 14 minutes, I'm going to try to pull a rabbit out of the hat and teach you meta-analysis. Woo! Okay. It's going to be this is the crash course in meta-analysis. And considering that I'm still learning more about meta-analysis and have been doing it for, no, I'm not going to admit how long I've been doing it for, but I count it in decades, not years. So that'll give you some indication. There's a lot here that you can learn. And so by necessity, this is the skipping the rock off the pond. And, you know, yes, I'm going to throw some formulas at you. But the goal here is to understand what the method's all about. Get the big picture, get the gestalt, really get a feel for, you know, when people talk about meta-analysis, what do they really mean by that? What are they talking about? And so that's what I'm going to try to accomplish, and hopefully we'll get through most of it. I've got a few slides that I know I'm probably going to skip over. So just forewarn you, I put a few more in than I think we'll need. They get into some more advanced topics. I find it useful to start at the end. And then we can all go get coffee or something, because we'll be done. No. Okay. In a sense, you can think of a forest plot as the end game for meta-analysis. It's one of the common sort of outputs of a forest plot. And here's one on the effects of cognitive behavioral programs. This isn't very descriptive. These are for criminals, trying to run criminals through about a 14 or 20-week group-based cognitive behavioral program, and then looking at whether it reduces future recidivism. And this is very bare bones. We see on the left you have each study. You know, Porporino and Robinson, 1995. Each row is a study. You have that diamond there, which represents the effect size for the study, the finding, what that study found. And that study found an odds ratio, we'll talk about that in a moment, that's really close to 1, meaning no difference between the two groups, but a little bit on the positive side. Small benefit. The horizontal line is a 95% confidence interval, clearly includes sort of the null value of no effect. Not terribly interesting there, but that's what we've got the line for giving an indication of precision. You know, we see at the bottom there are a couple of studies with fairly large positive effects. This Ross one at the bottom has an odds ratio of 10. So the cognitive behavioral group had an odds that was 10 times lower than the other group of recidivating. But look at that confidence interval. It's huge. This is a small study. Right? And as meta-analysts, we say, well, what's the general pattern of effects? Well, notice every single one of these studies is positive. Well, that's interesting. If this treatment had no effect whatsoever, we probably wouldn't expect all of them to be positive like this. We'd expect sort of it to bounce around, some positive, some negative. And with the exception of this one that's sort of really just out in left field, that, man, they practically found a cure for crime. There's variability, but it's sort of a consistent-looking pattern. And then as meta-analysts, we say, well, let's actually, you know, crunch some numbers here and come up with an average. And so at the bottom, we have the mean, which is that bottom diamond, of 1.5. So a 50% reduction in the odds of recidivating. Not bad. It's a meaningful effect. And a confidence interval around that, probably going from about 1.25 to 2. Doesn't include the null value of 1, so it's statistically significant. So this would suggest a statistically significant benefit of cognitive behavioral programs in reducing recidivism among offenders. That's kind of exciting. Right? Now notice, how many of these studies individually were statistically significant? Well, let's quickly count. Those are the ones that do not have a confidence interval around 1. It looks like only 2. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 studies, 2 of which were statistically significant. 7 of which were not statistically significant. Yet we're concluding that this works. Interesting. We're going to come back to that point in a moment. But this is sort of where we're going with meta-analysis. Okay. So here's the overview of today's talk. I'm going to focus a little bit on the logic of meta-analysis. We've just started with that, and I have a little more to say about the logic of meta-analysis. We're going to talk a little bit about effect sizes. What are they? Some common types. We're not going to get into the computation of lots of effect sizes. I spent an hour and 15 minutes talking about that this morning. And so if you really wanted that, that was the advanced topic. And even the hour and 15 minutes wasn't enough time. But we'll at least touch on it so you get a sense of what they are. And then we'll focus on sort of the basic types of meta-analysis, analysis issues, coming up with the mean effect size, its confidence interval, looking at issues of variability. We'll at least introduce the idea of random effects versus fixed effects. There was a whole advanced topic on that earlier this morning. But you should at least know what the basic issue is. And I'll try to introduce, this is where we may have to crunch things a little bit, introduce at least the concept of moderator analysis. Though at some level that's an advanced topic. But you should be aware of what it is and have the concept. And then hopefully I'll have time for a few notes about software, of how to go about doing this. Because I'm not teaching you the software. I'm just trying to give you the conceptual orientation about what this is all about. Okay. That sound like what you're hoping for? Yeah. All right. Okay, good. Because that's what I came prepared for. So if you want something different, I'm going to have to change gears pretty darn fast. But that's what I got here. The logic of meta-analysis. Whoops. This is not easy to walk in and out, and I have a tendency of doing that. I'm going to have to be careful here. Traditional narrative reviews, or sort of non-meta-analytic approaches to reviewing the literature, thank you, tend to focus on statistical significance. And that's problematic, as I'm going to talk here in a moment about the weaknesses of statistical significance. And they often tend to lack transparency. Now we have this broader term called systematic reviews that meta-analysis is now sort of often embedded in. And that whole process of systematically reviewing literature is focused very much on the issue of transparency and replicability. So that the nature of the review is not just that, I'm a really smart guy. I read these 24 studies. And as an expert, this is what I think these 24 studies say. And really, that's traditionally what a lot of sort of scholarly reviews were all about. It was all about this sense that, well, I'm a scholar, and so this is my opinion after having carefully thought about and looked at this literature, and you just sort of need to take it on faith that I somehow did this in my head the correct way. Well, one of the problems with that approach is statistical significance has a tendency to lead you astray. It has its values. It's quite useful at the primary study level of making sure, and unfortunately this example is going to date me, that you don't end out on the cover of Time magazine saying you've discovered cold fusion. Okay. It's the protection against, yeah, a few people got that. There was really somebody who thought they discovered that and was on Time magazine back in the 80s, yes. It's protecting you against sort of getting excited that you found something that could be explained by chance. That's really important and it's valuable. But once you start looking at results across studies, it has a tendency to trip you up. Because there's an asymmetric relationship between a significant finding and a non-significant finding. If you have a statistically significant finding, that's a strong conclusion. You can take that to the bank. Okay? If you have a statistically non-significant finding, that's a weak, wishy-washy finding. Okay, most people forget this after their first semester of statistics, but first semester of statistics, when you're writing out all of those hypotheses things, fail to, reject the null hypothesis. Well, when you can't reject the null hypothesis, you were supposed to write this rather convoluted phrase. Thank you. Fail to reject the null hypothesis. Wait, doesn't that mean accept the null hypothesis? No, it doesn't mean accept the null hypothesis. It's wishy-washy. Well, the null might be true, it might be false, but we can't say that it's false, so okay. Now, In front of you, you have a collection of non-significant findings and significant findings, and you put them on a scale. How do you balance these strong conclusions with these weak conclusions? If you know the answer to that, you're smarter than me. Okay. I can't figure out how you would do that. But reviewers somehow manage to do this all the time, sometimes by counting it up. And so if we back up a few pages, if I can manage to do this way, they would say, you know, in this area there were 7 studies that had null findings, 2 that had positive findings, so we need more research. The conclusions are equivocal. And sure enough, there's a grand history in clinical psychology of review after review after review calling for more research. And the more research that's done, guess what happens? If you're focusing on statistical significance, the more equivocal the results appear to be. Because the larger the pile of non-significance, the larger pile of significance, and these two piles just keep growing, you will pull your hair out. Okay. So maybe there's a problem with focusing on statistical significance. So meta-analysis says, you know, that's not what we're interested in anyhow. Statistical significance is just this abstraction. It's the probability of our results in a world in which the null were true. But of course, we don't believe the null is true. So, I mean, it's this very artificial abstraction, useful in a very narrow sense. But it's not what we're interested in. What are we interested in? We're interested in what we're studying. What's the effect? What direction is it in? Does cognitive behavioral program for offenders reduce crime or increase crime? And if it reduces or increases, by how much? That's what we really want to know. So why don't we focus on what we really want to know? Let's focus on the magnitude and direction of effect. Meta-analysis shifts our focus to that. And that says, well, you know, maybe we should also approach doing a review as a research project in its own right, and approach it with the goals of being transparent, replicable, etc., so that others can evaluate the nature of our work. And so then what meta-analysis does is actually focus on those effects, which we call effect sizes in some generic sense. And it wants to look at several important things. Well, what's the average effect? That's interesting. On average, do these programs reduce crime? Well, I say yes. Of course, then you might come back to me and say, well, yeah, but do they consistently reduce crime? So we might be interested in the consistency of the effects. Maybe some reduce crime more than others. And so we might want to look at that variability. And in looking at that variability, we might want to look at it in relationship to study features. You know, maybe it's studies that were done in prisons were more effective than studies done in jails, or with certain types of offenders. Maybe violent offenders, these programs are particularly useful, but those darn property offenders, really high-volume criminals in general, are just a bugger to try to convince to stop committing crimes. Who knows? There might be all these sorts of relationships. So the focus is average effects, and then consistency of effects, and possibly explaining inconsistency in effects. And so the methods that I'm going to sort of work us through all have to do with getting at these three things. All right? So how do we go about doing this? Well, the first thing is we need that effect size. We need that thing that encodes our finding in terms of the magnitude and direction. Well, it has to put it on a numeric scale. We don't want something that says, you know, small effect, medium effect, big effect. Right? We need a number, so we're going to do statistics on it. It must be comparable across studies. You know, if on one study I calculate this number and I come up with 0.25, another study I calculate the number and I come up with 0.225, those should be sort of comparable size effects. If I come up with another one that's 0.4, that better be a bigger effect and not a smaller effect than the two studies that were 0.25, right? These sort of bigger numbers should be bigger effects, smaller numbers, smaller effects. It needs to be independent of sample size. Notice we're not studying how many participants the researcher was able to recruit into their study. What we're studying is how big's the effect that they found, you know, the phenomena, the effectiveness of this program, not how many people were in the program. Right? And the other quirk is we have to be able to figure out its standard error. Well, standard error is a statistical measure of its precision, and if we're going to look at consistency of effects, we have to know how precise the effects are in the first place. Right? That's what those confidence intervals were all about, is the precision, and we need to know that. Now, there are many different effect sizes. When I say effect size, I'm not referring to a specific statistical parameter or statistic. I'm referring to anything that sort of satisfies these criteria. I think I can probably think up about 12 or 14 of these off the top of my head. And you know, some of you might come up with research situations where you create your own effect size as long as it satisfies the necessary criteria. And for each effect size, as you'll see, there's often more than one way to calculate it, depending on the information provided in the primary study. One of this, there's two listed here. So I should say 4 of the most common effect sizes used in meta-analysis are the ones listed here. The correlation coefficient. Hopefully all of you, you're sufficiently familiar with statistics to know what the correlation coefficient is. And it's a nice standardized effect size, right? You know, it ranges between -1 and +1, and is useful just in its form as a correlation coefficient. And we're not really going to talk about that one because it's not particularly widely used in the work in the Cochrane or Campbell collaboration, though it's widely used in meta-analyses in social psychology, psychometric work, etc. The standardized mean difference, sometimes you'll see this referred to as D, Cohen's D, G, Hedges G. For our purposes, it's all pretty much the same thing. Right? And I'll explain what that one is here in a moment when you use it. The other two that are quite similar and used in the same situations are the odds ratio and the risk ratio. And I believe, I'm going to have to remind myself here of my slides. Yes, okay. Apologize for that flipping. I know that can be confusing. One of the challenges of meta-analysis, and something that will take you a lot of time, if you were in here the workshop prior to this, Sandra Wilson was talking about coding effect sizes, coding studies. Well, one of the big parts of coding studies is often calculating effect sizes. It can be a lot of work. And you must compute the effect size from the information provided in the primary study. This might be from t-tests and p-values, descriptive statistics, etc. You might also need to manipulate the data that they provide. You might need to collapse across subgroups. Common example in my situation is I get a lot of studies in the criminology field that they'll have a comparison group and they'll have the treatment group, but they'll report the data separately for the people who successfully made it through the treatment group and the people who dropped out. Right? And now the results are always wildly successful for the graduates versus the comparison group. Well, of course they're successful. They successfully graduated, and success breeds success. There are other, and this was part of this morning's advanced meta-analysis, some of the ways of calculating some of these statistics just algebraically equivalent to other ways. Computing the standardized mean difference from mean, standard deviations, and sample sizes is the same as getting it from a t-test. But estimating from binary data is an approximation. And you need to be aware of these sorts of things. And sometimes, you know, no matter how hard you try, you just can't squeeze an effect size out of some studies. The more you do this sort of work, the more creative and clever you get, but some studies you just can't do. Standardized mean difference. Here, the fundamental relationship is a group contrast, treatment group, control group, boys versus girls, drug A versus drug B, drug A versus a placebo, etc. And the outcome is sort of conceptually a continuous dependent variable. Depression, self-esteem, something that might be measured on a multi-item scale, or fundamentally, something where it would be statistically appropriate to calculate a mean. All right. In a sense, in its simplest form, if this data is data that's appropriate to calculate a mean, or essentially the construct of interest, then the standardized mean difference might be the appropriate effect size. But different studies have different outcomes. One study might have the Beck depression inventory, another the Hamilton depression inventory. These are on different scales. How do we make them comparable? Well, through standardization. This is the same sort of standardization that occurs in the correlation coefficient, okay, by using the normal distribution. And so we use the raw standard deviations within each group to look at the normal distribution and examine how much the means are different from one another in terms of the normal distribution. Hence the name standardized mean difference. Now, this can be computed from a variety of other information. From a t-test, okay, it's that top formula where you're just essentially working out, removing a component in the t-test that's a function of sample size. That first one is algebraically equivalent. If you did this computation with the t or with the raw data, you'd get the same standardized mean difference, or d. From a correlation coefficient, you can also get d. A dichotomous outcome, this is interesting. You might have some studies that instead of measuring depression on some scale, they just group people into you're depressed, you're not depressed. Okay? Oh, darn it all. I'm going to have to throw them out. That would be a waste. Wouldn't it be nice if we could actually calculate the standardized mean difference from that study and include it with all the other studies in our meta-analysis? Well, guess what? You can. But it's an approximation. It's not exactly what you would get if they'd given you means and standard deviations. A bunch of Monte Carlo simulations shows that it works pretty well in most situations. And here's this computation. I'm not going to explain all of the terms, but the A, D, B, C in there are the cell frequencies of a 2x2 frequency table. And essentially what you're doing is you're rescaling an odds ratio from the logistic distribution to a normal distribution. Pretty cool little trick. And it works fairly well. Let's see here. I should have pulled it up already. There's an effect size calculator on the web that I've created. That has lots, this list here is all the different ways that you can calculate the standardized mean difference. So we've got from a chi-square, the p-value of a chi-square, unstandardized regression coefficients, gain scores. There's all sorts of these. You click on it, and it'll give you a little table, you plug in the appropriate data. That calculator is available both on the George Mason website and on the Campbell website. All you really need to take away from this discussion on the standardized mean difference at this point is not, remembering or trying to remember all these formulas. Even statisticians don't bother memorizing formulas. You always look them up because you want to make sure you get them right. Now, sometimes you use them so often that, you just kind of remember them. But that's not the point with equations. What you need to realize is there's a whole category of equations that help you take the information in the studies and try to squeeze it through some manipulations where you spit out a standardized mean difference. The correlation coefficient, we're not going to talk about it much, but it's for situations where you essentially have two continuous constructs, inherently continuous constructs. Say the relationship between GRE scores and performance in graduate school, which, by the way, isn't a very strong correlation. But of course, in part, that's because most people with low GRE scores don't get into grad school. Okay. The odds ratio is widely used in medical meta-analyses because lots of their outcomes are dichotomous. And that's a situation where you would use the odds ratio or the risk ratio. We've got a group contrast and a dichotomous dependent variable. Pregnant, not pregnant. Alive, dead. They were cured, they weren't cured. Okay. These sorts of success, failure, treatment group, control group. So we get a traditional 2x2 frequency table. And it's very easy to calculate the odds ratio with that little formula right there. Now, with the odds ratio, if you spend some time thinking about it, there's only so many ways that you can report the results for a dichotomous outcome. The frequency, the percent, the proportion. I mean, you quickly run out of options. So the reality is this one tends to be pretty straightforward because there's really a limited number of ways that people might report it. So the number of ways of trying to compute your effect size is limited and tends to be fairly straightforward. Okay. The goals of meta-analysis then are sort of to describe this effect size distribution. So what you should be imagining is that you've decided what type of effect size to use for your meta-analysis. You've decided that the fundamental nature of my meta-analysis, the nature of the relationship I'm interested in, lends itself to the standardized mean difference. So I'm doing a standardized mean difference type meta-analysis. And so now you've calculated a whole bunch of standardized mean difference effect sizes on your collection of studies, and you now want to describe that distribution of effect sizes. So you might want to calculate the mean. You might want to put a confidence interval around that mean. You might also want to test whether it's significantly different from 0. Though we probably don't want to obsess too much over significance levels, having just criticized statistical significance testing in the first place when we started down this path. Right? We might want to test the consistency of the effects. Are these studies telling a consistent story with one voice, or is it a chorus of multiple voices? Right? And if it's a chorus, well, maybe we should try to explore and see if we can identify some of those individual voices. So this is our goal with these methods. Now, here's the problem. In the early days of meta-analysis, people said, well, this is data just like any other data, so let's just throw it into all our standard programs that we are accustomed to using and analyze it. Let's just throw it into regular regression analysis. We just calculate a mean, have SPSS tell us what the standard error is. Woo-hoo! Away we go. Well, those analyses assume something that statisticians called IID, independent and identically distributed data. Wow, that's a mouthful. Well, it means that the data is independent. Well, we still assume that here. But identically distributed, what the devil does that mean? Well, it means that each data point has roughly the same level of precision. So if I give everyone in this room sort of a, oh, I wouldn't be crazy enough to get satisfaction with this course, but let's say I was crazy and had you fill out satisfaction form with this course, the presumption is that the scores I'm getting from each of you are all sort of roughly of equal precision. Well, with meta-analysis, that's clearly not the case. Effect sizes from some studies are more precise than effect sizes from other studies. We might want to give those effect sizes from the larger, more precise studies more weight. Give them a louder voice than the studies from the really small pilot studies. Well, so people said, yeah, we do. So let's do sample size weighting. It's not a bad solution. But Larry Hedges came along and figured out it's not optimal. And in statistics, we actually have a direct measure of precision. It's called the standard error. So why don't we weight by the standard error, or the inverse? Because the problem is the standard error, the smaller it is, the more precise. So if we weighted by the standard error, we'd be doing the opposite of what we want. Well, in math, if you want to flip something so you're doing the opposite, you take the inverse, right? But what Larry Hedges determined was it's actually the inverse of the standard error squared. Well, a standard error is a type of a standard deviation. If we square a standard deviation, we have a variance. Thank you. A few people are still awake. All right. So we call this inverse variance weighting. All right. So the type of meta-analysis that I'm teaching you is formally called inverse variance weighting meta-analysis, or inverse variance weighted meta-analysis. Right. And once we start using the inverse variance weight, we get all kinds of statistical benefits. Because now, if we've got this measure of how precise any of the individual effect sizes are, we can probably come up with something that tells us how precise our mean is. Yeah, sure enough, it's really straightforward. And we can also then very easily, through some little statistical manipulations, figure out how consistent, create confidence intervals, create an index of how consistent our effect sizes are. Okay. Unfortunately, we're not quite ready to jump into meta-analysis yet. We've calculated all these effect sizes, and we want to analyze them. But a lot of them, they still need a little fixing up to be ready to go to the prom. All right, they're not quite ready yet. So some of them we got to do a little tweaking to. The standardized mean difference, it's got a little bit of bias in it. It's a little bit too big when the sample sizes are small. Well, there's a formula that corrects for that. That's this first formula. You don't have to understand it. It just, if the sample size is small, it punches it downward just a little bit. Not much, just a little bit. And as the sample size gets bigger, the adjustment starts going out into the third, fourth, fifth, sixth digit, into where you really wouldn't care about it. But it's easy to do. It's just a little simple math right there. So we apply this correction to all effect sizes if we're doing the standardized mean difference. And then you get to say, I'm using the unbiased standardized mean difference estimator. Right? Okay. So that's pretty cool. So you just, remove this bias. The correlation coefficient, we can't calculate the standard error. Right? It doesn't have a standard error formula. But if you take the correlation coefficient and convert it using Fisher's Z transformation, you now have an easily solvable standard error. So we'll just use that in its standard errors. The odds ratio and the risk ratio as well, it's an odd beast. And it also doesn't have a standard error. Keep in mind that an odds ratio of 1 is your no effect. Everything from 1 to 0 is a negative effect. Everything above 1 to infinity is the positive effect. Wait, that's this big arm over here, this little arm over here. It's asymmetrical. Well, if we simply take the log of our odds ratio or the log of our risk ratio, we then get something that has an easily solvable standard error. So that's what we're going to use for analysis. For those of you who are going, that statistical stuff just went over my head. The simple thing to realize is you've calculated your effect sizes, and now sometimes you got to dress them up a little bit to get them ready for analysis. Okay. So now we've cleaned them up. They're ready for the prom, almost. We need our standard errors. Now, more formulas, I know. I'm sorry. This is supposed to be the basics course. You're going, this is the basics course. I thought formulas were the advanced course. The non-formulas were the basics. I'll tell you what you need to know from these formulas. Okay? All you really need to be paying attention to is in almost every case, it's mostly about sample size. All right? So look at the first one for the standardized mean difference. We've got n sub 1, n sub 2, n sub 1, n sub 2. Those are sample sizes. As a matter of fact, if the standard deviation, the effect size, ES under sub SM for standardized mean difference effect size, if that goes to 0, that whole term goes away. Right? So it's about sample size. Oh, cool. The correlation coefficient, 1 over the square root of n minus 3. That's entirely about sample size, right? The odds ratio, A, B, C, and D, those are the cell frequencies of the 2 by 2 table. Well, if we add up A, B, C, and D, we have our total sample size. Oh, it's about sample size again. Now, for the weight, for meta-analysis, it's 1 over each of these standard errors squared. Okay, so that's our weight. We need a weight for our effect size. And that this weight, it doesn't equal sample size, but it's a function of sample size. As sample size gets bigger or smaller, this weight's going to get bigger or smaller. We're almost ready. Almost there. Everybody's gotten dressed up for the prom, but guess what? Not everybody gets to go to the prom. Some have to stay home. Why is this? Well, actually, we have to maintain statistical independence. So if one study had 3 or 4 effect sizes, another study had 1 effect size, another had 20 effect sizes, and we just let all of them come to the prom, some studies are going to have a very loud voice, a little deafening, and it's going to violate all sorts of statistical assumptions. So we can only let 1 effect size per study come to the prom. Well, that's a bummer. But the good news is we can have more than 1 prom. We can have proms happening in different rooms, right? Different analyses. We can look at depression as one, that prom's happening in one room. We can have, say, anxiety happening in another room. Right? Nobody's anxious about proms, right? Okay. We can have different effect sizes going into different piles. But for each sort of analysis, only 1 per study. Or there's a little parentheses, per independent sample. Okay. The idea here is they have to be statistically independent. So if you have a study that's actually reporting on 3 different sub-studies, it's 1 for each of those sub-studies, or completely independent groups, okay, you can keep that separately. But you just have to have this mind sort of, in your head, sort of 1 per study. But you can do lots of different analyses to make use of all those different ones by putting them into different piles. Okay. We're almost there. So we've got our studies. We've pulled out all these effect sizes. We've calculated the effect sizes. Then we got them ready. We cleaned them up. And we calculated their weights. And now we pulled out an independent subset that answers one of our research questions. Now we're ready to go. Okay? So the first thing we're going to do is calculate the mean. The average. And literally, it's just the average, but it's a weighted average. So rather than just adding everything up, dividing by the number of numbers, we multiply each value by its weight and divide by the sum of the weights. It's a standard weighted average. If you remember doing those in statistics, though quite frankly, this is one of those things that you would have found in statistics books from the 30s, 40s, 50s, and 60s, and seems to have dropped out since the advent of the personal computer for some reason. But fairly straightforward formula there. So that gives us our mean effect size. Now, here's the cool thing. We now want a measure of the precision of that effect size so that we can calculate a z-test and confidence intervals. Well, remember that that weight is based on the precision of the individual effect sizes. So maybe our mean is a function of those weights. Well, sure enough, if you add up all those weights, take the inverse, you've got the standard error of the mean. Now, how cool is that? If you were just doing sample size weighting, this wouldn't work. Right? This is what you get by using that inverse variance weight. That's pretty cool. And once we have a standard error, we can do really cool things. We can create a confidence interval. Right? And this is just standard methods of creating a confidence interval. There's nothing unique to meta-analysis here. If we take our standard error times 1.96, gosh, where did that 1.96 come from? I've seen that number somewhere before. 1.96, 1.96. You remember where that number's coming from? I hear people muttering. Huh? Yeah, of what? Of what distribution? The normal distribution. it's just shy of 2 standard deviations. It's the point at which there's 2.5% in each tail. It's that 0.05 significance level for the normal distribution, right? Okay. And so we can create our upper and lower confidence interval using that standard formula. And we can also do a z-test on our mean just by taking our mean divided by the standard error. That's also just a standard way of calculating a z-test. So wow, with some fairly simple statistics that you can do on a calculator, we've calculated our mean effect size, we've calculated the standard error, we've created confidence intervals, and we've done a z-test. Nothing more than a few simple computations. Now, I should have picked an example with standardized mean difference because it's a little easier, but this is fine. This is that first example with the cognitive behavioral. And here are the studies. We see the sample sizes. We see all of our odds ratios. Here was that one that was close to 1. It's 1.08. Here's the one that was really large, 10.29. Now remember, we had to analyze the logged odds ratios, so those are all here. And there's the weight. Okay. And so we could, by hand, go through those computations, or we could let a computer do it. Okay. Here I'm using macros that I've created for Stata. I have versions of these for SPSS, Stata, and SAS. You can also use RevMan. You can use Comprehensive Meta-Analysis Program. I'm trying to think what other. Those are the main ones. There's also programs that others have created. And to quickly walk through just a few of the things, it's telling us we've got 9 observations. And the fix, I'll explain. Right now, we're just doing fixed effects. It's telling us that our mean is 0.37. It's giving us our confidence interval, our standard error, our z. And from the z, we could figure out the p-value. Well, we've just figured out how to calculate that whole row. We haven't figured out everything else on this page yet. We'll get there. But we've just figured out the math behind that whole row. This is the same thing, but it's converting it from logged odds ratios back into odds ratios. Just undoing the log, taking the anti-log or the exponent. Okay. So we've calculated the mean effect size, put a confidence interval around it, done a z-test. But really, we should be asking, are these studies telling a consistent story? Is it homogeneous, or is there heterogeneity in these findings? So there's something called the homogeneity analysis test. Now, it probably should be called the heterogeneity test, because when it's statistically significant, it's heterogeneous. And I've had some people, when it's statistically significant, say, oh, it's homogeneous because it's the homogeneity test. Well, no, it works the other way. And it's testing the assumption that all of these studies are estimating a common effect. In other words, that the only difference across these effect sizes is sampling error, as opposed to true differences across the studies. If homogeneity is rejected, so in other words, we have heterogeneity, that single mean effect size is not really a good representation of all of the studies. It's, in a sense, an oversimplification of this research literature. Because it means that there are real differences across the studies, that the studies are finding real differences between them. Well, you've got a couple of options. One, you can try to model that difference. You could fit a random effects model. Going, oh, no, I thought this was the basics class. Well, we at least have to understand the concept of the random effects. And you'll see why in a moment. Or you can try to do both. You can both assume that there's some random effects, and you can try to analyze differences across studies. Homogeneity analysis. It's really not that scary. Presenting 2 formulas here. The first one, for those of you who like formulas, might actually be able to understand what's happening in the formula. Right? The first one saying if we take each effect size minus the mean and square it, well, that squaring gets rid of the negatives, puts everything positive, right? Okay. Oh, well, okay, we're figuring out how far each of the studies is from the mean. And we're adding it up. But we're weighting it because everything's sort of a weighted analysis. A big difference from a large difference from a study with a large sample size should matter more than a large difference from a really small study. Really small study, yeah, those are going to bounce around more, so those differences shouldn't count as much. Now, that looks a lot like the numerator in the formula for the variance. Yep. Formula for the variance, if you remember, brush off that part of the brain that you had somewhere where somewhere you've all calculated standard deviation or a variance. In the top, it's each score minus the mean squared, added up. Then you eventually divide by n minus 1, take the square root. That top part is how much each score varies from its mean. We call these the sums of squares, that top part. We're summing the squared deviations around the mean. In this case, it's a weighted sums of squares. Now, that formula is a real pain in the neck to do by hand. So there's a computational formula, just like with the standard deviation. There's a formula that looks just like this that's for use when you're doing it by hand. It's a lot more precise by hand. But it gives you the same answer as that first one. This is distributed as a chi-square. So you use the chi-square distribution to figure out whether it's statistically significant. And the number of the degrees of freedom is simply the number of effect sizes minus 1. And in meta-analysis, we use k to indicate the number of effect sizes, because if we used n, it gets too confusing because you've got the n in the studies, and then you've got the n in the effect sizes, and that's just, so we've decided to use k. I don't know who picked k, why they picked k. We've settled on k. We use k. It works. K equals number of effect sizes, right? It's different than D. It's not G, right? Okay, so it was available, you know? Now, let's see here. So the Q statistic, if it's statistically significant, it indicates that, yes, you have heterogeneity. But there's a problem with it. It tends to be underpowered when you have a small number of studies. So you might then be tempted to say, oh, this distribution's homogeneous, when it really isn't. Because keep in mind, this is just like a null finding in any other context. Just because Q is not significant doesn't mean everything is homogeneous. It just means you're not sure it's heterogeneous. And so Julian Higgins developed an alternative index called I-square. Why I? I don't know. Another available letter, apparently. Now notice that it's mostly a function of Q. And any time Q is bigger than its degrees of freedom, you at least have some excess variability beyond what you would expect simply by chance. And so this is just an index of how much excess variability you have relative to, you know what? I think the denominator is supposed to be degrees of freedom. I'm going to have to check that for you. I'm looking at that and suddenly it looks wrong. But the concept is the same. You're looking at how much beyond your degrees of freedom you are. And the general rules of thumb is if you've got 75%, if I squared is 75% or larger, you got a lot of heterogeneity. 50% or larger, moderate heterogeneity. 25%, you're at low sort of heterogeneity. 25, yeah, something like that. If you're in those ranges. And this is useful when you're doing a small meta-analysis as an alternative to Q. Now, unfortunately, I've misled you all. The version of meta-analysis that I've just shown you is what we call fixed effects meta-analysis. And we actually don't recommend you do fixed effects meta-analysis. Oh, no. We recommend that you do random effects meta-analysis. But it's really hard to start with random effects meta-analysis. It's a lot easier to learn random effects from the fixed effects. So what am I even talking about here? Okay. Well, fixed effects meta-analysis essentially assumes homogeneity. Fixed effects meta-analysis assumes that all of these studies are estimating a common treatment effect, and that any differences in those effects is simply due to sampling error. Now, one could imagine situations where this assumption would be reasonable. If you are doing pure replications. I'm a social psychologist. I'm running this, doing this little lab study where I bring college students in and I deceive them about something, and then I do this groovy little thing and I measure their performance on something. And 5 or 6 of my colleagues at other universities do the same exact study. Identical. Same measures, same research design, everything is the same. We wouldn't expect those results to be identical at all 6 universities. We'd expect, but we would really expect that that underlying relationship should be the same. And whatever difference there is should just be the particular sample of students that they happen to draw from this population called college sophomores, who've been widely studied by social psychologists. We know more about college sophomores than any other aspect of the population. Okay. But once you move away from pure replications, this logic starts to fall apart. You say, well, you know, this cognitive behavioral program with offenders, not all of these teachers are going to implement it in quite the same way. Some are going to do a better job than others. And sometimes it's being implemented with only violent offenders, sometimes with a general offender population, sometimes only with property offenders. In each of these cases, the effect, the underlying effect, the true effect, if we were God and knew what that value was, might bounce around. So maybe our effect sizes have variability in them that's sampling error plus some variability from true study differences. These 2 pieces instead of just the one. Well, that's what the random effects model assumes. Unfortunately, it also assumes that these random effects are normally distributed. Now, we are not able to prove that they're normally distributed, and when statisticians start debating the random effects model, they go off on these tangents about how credible that assumption is. But the logic is fundamentally here that now we're assuming that really there are genuine differences across these studies in terms of the underlying effect, and so our statistical model should incorporate that variability. This is where some people who say, you know, the studies I'm combining, I don't think you can combine them because they're too heterogeneous. Well, there is a point at which studies are so heterogeneous that it's conceptually meaningless to combine them. But statistically, this model assumes heterogeneity and allows for that to be incorporated. Okay, so the variability in effect size is now assumed to be due to both sampling error plus variability in those true effects that are being estimated by these studies. Now, why to use the random effects model? One, the assumptions are just far more plausible for most of the research any of us would be looking at. Unless you're simply analyzing research that are fairly pure replications, really the random effects model represents a more plausible sort of a set of assumptions. Now, the other cool thing is that as your effect sizes become homogeneous, the random effects model converges on the fixed effects model. Well, that's kind of cool. So, you know, as the whole distribution becomes homogeneous, eventually we get the fixed effects model. So the bottom line is use the random effects model. The policy of the Campbell collaboration is to either use the fixed effects model or report both. I mean, the random. Wow, apologies there. Use the random effects model. Report the random effects model. If you're uncomfortable with that, you can report both the random and fixed effects, but you may not only report the fixed effects. And the Cochrane collaboration, I believe, has a similar policy. That you can report both, but you can't just go with the fixed effects because the assumptions just aren't plausible. So you're going, well, darn, you taught me how to do the fixed effects. Now you're telling me to do the random effects. Don't worry. It's not that different. We just need a new set of weights. Remember, our first set of weights were a function of sampling error. The fixed effects model assumes that variability is due to sampling error. The random effects assumes that variability is due to sampling error plus true differences. Oh, so maybe if we come up with a weight that is sampling error plus the variability, the true variability across effect sizes, we'll be able to capture this. Yes, that's exactly what we do. All right? So we need a set of weights that are now a function of both sampling error plus study level variability. Well, we've already got the sampling error piece, so we now just need that study variability piece. Where are we going to get that from? Maybe from Q. Q is our measure of heterogeneity. So maybe if we calculate the study level variability using Q, we can make this work. Sure enough, there's this thing called tau squared. Another available, apparently this was an available Greek. Very charming individual, apparently. And this is our estimate of the study level variability. And notice that it's mostly a function. There's Q right there, Q in the numerator. Right? And the weights are in the denominator. It's a measure of our study level variability. Now, when the distribution becomes homogeneous, Q goes to 0. Now, mathematically, when you're calculating this, if Q is smaller than the degrees of freedom for Q, it can go negative. Is it possible to have a negative variance? Can you have negative variability? Come on, someone. No, thank you. You can't have negative variability, right? So Q, the smallest it can get is 0. Right. Well, when it's 0, we have a fixed effects model. Right? And so now what we do, we take we recalculate the weights. We take all those standard errors we had calculated. We square them to get our variance. Then we add this constant that we counted that's going to be the same for all studies. We add that to our standard error, then take the inverse, and we've got our new weights. So now we have our random effects weights. Well, what do we do at this point? Well, we just go through all those same equations that we went through before. A weighted mean. We have our random effects mean. Add up these new weights. Take the square root, divide by 1. We have the standard error of the random effects mean. Now, those who are good at math are suddenly going to go, that standard error is going to get fatter. Yep. Or going to get bigger, going to create a fatter confidence interval. Yeah, we're assuming additional uncertainty in our mean. So the confidence interval is going to get bigger because we have more uncertainty, but it's also more realistic. So we just recompute using these new weights. You've got your random effects meta-analysis. That wasn't so bad. Okay. And actually, I'll go up here to, yeah. And that's what you see here. Now, the other thing that I've sort of oversimplified, there's really more than one way to calculate that tau squared. I showed you one method. There are a bunch of others that use maximum likelihood and all kinds of really nasty statistics. Okay, and they have their advantages and disadvantages in different situations. And right here we've got two different methods, and you can see that the mean changes a little bit. But look what happens to those confidence intervals in the standard error. The standard error gets bigger in both cases. The confidence interval gets fatter, but it's still statistically significant. So in this case, and we've got our Q statistic over here, which is not quite statistically significant. So in this study, one would say, we can't reject homogeneity. These effect sizes are fairly, telling a fairly consistent story. Remember, there was just that one study that was sort of really way out of line. Everything else was telling a fairly consistent story. But even if we assume random effects, we still get a statistically significant overall effect, etc. Okay. Now, where are we here? Now, in a nutshell, that's really the bare bones meta-analysis. All right? A bare bones meta-analysis is just going to look at the average effect, it's going to look at its confidence interval, and it's going to look at at how homogeneous or heterogeneous it is. And there are a lot of meta-analyses that stop at that point and then create a pretty forest plot to look at, like we saw at the beginning. But particularly if you've got enough studies, you might want to start asking whether or not we can explain some of this variability. If we can account for it with study features that we've coded. Sandra was teaching those of you who were here the previous hour all about how to code. So hopefully you've extracted information about how your studies are different from one another. And you can use that to try to explain these differences. And really, there are two ways to think about doing this, conceptually and statistically. One is through a categorical model, basically where you put effect sizes in different piles, and you look to see whether those piles are different. If you've just got two piles, with this cognitive behavioral treatment programming, the thing that I didn't show you is it's actually two different programs. Moral recognition therapy and reasoning and rehabilitation. Two very similar but still somewhat different cognitive behavioral programs. And I might want to know whether one of these programs is more or less effective than the other. So put all the reasoning and rehabilitation effect sizes in this pile, put all the moral recognition effect sizes in this other pile, and compare the means. And so that's, in that case with just two, that's a lot like a t-test. Don't use a t-test. We have special statistics for doing it. It's called analog to the one-way, to the ANOVA. It's a lot like a one-way ANOVA with only two categories, like a t-test. But you could have three piles. There might be a third category of programs or a fourth type of program. You might have four different types of treatment programs. Or maybe it was offender types. Maybe you had the violent offenders, the property offenders, and then some studies were just general prison population. Okay. So now I got three piles, I got three means, and I want to compare across those. That's sort of a categorical approach to moderator analysis. And we have methods for doing that. Now, sometimes your study level characteristics might be more continuous in nature. Maybe you have a measure of degree of implementation. Right? How well they implemented the program. That was, crappy, pretty bad, not so terrible, almost good, and good. Right? Okay, and you want to see whether or not that relates to effect size. And you don't really have enough to, so you want sort of this linear regression sort of approach. Sure enough, we've got meta-analytic forms of regression. Lots of people incorrectly just throw all this stuff into regular regression. That's a no-no. You have to use what some people call meta-regression, or what I just like to call meta-analytic regression. And for both of these moderator analyses, you can do a fixed effects version or a random effects version. Once again, just start with the random effects version, because if you explain all that excess variability with your moderator variables, the whole thing just simplifies to a fixed effects for you, rather than running it both ways. Now, in the literature, you might see some people call these mixed effects models, and you're going, wait, I learned about random effects. What's the mixed effects? It's just a random effects moderator model. The reason they're calling it mixed is because the independent variables in your regression model are fixed factors. That's a technical distinction that you don't need to understand. Some people like to call them mixed models, some random effects models. For our purpose, it's not a meaningful distinction. How am I doing on time? I think I'm doing well. This is where I've got some slides that I don't have time for all of. So I'm trying to think what would be most productive here. Yeah. This is an example of a categorical moderator analysis. And in this case, it's actually this is a meta-analysis of domestic violence programs where we had 7 studies that were randomized and 7 studies that were not randomized. And notice here, categorically, we've got the mean, the standard error, the confidence interval, the z, etc., for each category. That's pretty straightforward. What a lot of people do incorrectly is they simply look to see whether each one's significant or statistically significant or not. Now, in this case, neither one is. But sometimes one of these will be statistically significant, the other won't be, and people will say, I've got a moderator effect. The program works for girls, but it doesn't work for boys, for example. If one row was girls and one was boys. Now, guess what? Sometimes the effects might be the same. It's just that one had a larger sample size than the other. Right? What you really want to look at is the Q-test between the two means, which is just like a t-test. And that's what's testing the difference between the means. And that's sort of your proper categorical moderator analysis that's telling you whether or not this categorical variable is accounting for some of that extra variability. Is it explaining some of the reason why you have noise in your data? Okay. Regression analysis. In this case, the effect size is sort of that dependent variable, and study features are the independent variable. Now, the cool thing here is you can have more than one study feature. So you could build a regression model with several study features. You have to have enough effect sizes for doing this, but you don't need quite as many as you would with typical regression. Don't use regular regression. You must use specialized software for this. You must use software designed for meta-analysis, and I'll talk about software here in a moment of where you can do sort of this stuff. But how this might look would be a result like this. Now, this bottom table of regression coefficients, this is, if you're familiar with regression, this should look pretty familiar to you. If you don't know regression, I don't have enough time to teach it to you. Okay. But if you know regression, we've got our unstandardized regression coefficient, a standard error, confidence interval, a z-test, p-test, the standardized beta. That's kind of cool, right? Well, the only other thing that's relevant is this model, homogeneity analysis. Well, the Q-test for the model is just like the F-test for a regression analysis. It's telling you whether or not your regression model is explaining variability in your data. So in this case, look at that. That model, it's significant at 0.002. So this model is explaining variability in effect sizes. Hey, cool. Okay. Then we can go down and look at which particular variables matter. And it looks like these two, TX var1, TX var2, which quite frankly, I don't remember what those are. But that's okay. They're independent. They're study characteristics, right? They're having something to do with the type of treatment from this analysis. So that's a moderator analysis. Because this is the basics class, really what you should be taking away from this is the conceptual framework that when we've got some effect sizes, we want to look at sort of the overall average. We'd want to look at its confidence interval. We'd want to look at how consistent it is, its homogeneity. And maybe, depending on our interest level, the number of effect sizes, etc., we might want to try to explore why some studies have larger or smaller effects using either a categorical moderator analysis or a regression-based moderator analysis. In a sense, conceptually, that's the bottom line here that hopefully you can take away from this. Now, the other thing in the remaining few minutes is a forest plot. It would probably take me an entire hour and 15 minutes to teach you how to create forest plots. And that would just be in one program, and then we take another hour in another program, and okay, because depending on which program, it would depend. But it's important just to sort of make sure you understand what they are. It's a visual representation of the results. It's what we started with. Now, the one that I presented was sort of a stripped down version. I wanted to make it as simple as possible. But some of the things that you would have a study label. Mine had that. It indicated the author and the year. Often you'll then have another column with other stuff, like the study sample size. Sometimes you'll see studies with other columns with maybe sort of the percent successful, percent unsuccessful. So you can imagine you might have several columns of information that you might want to present to your reader. But then that forest plot, the really pretty part, the graphic part, you're going to have something to indicate the effect size, a dot, a diamond, a square. Some forest plot programs make this bigger or smaller depending on the size of the weight. Some people think that's really cool because then the studies that get lots of weight get a lot of ink. Studies with very little weight get small ink. My diamonds were all the same size. Okay. You then have a horizontal line with a confidence interval. This represents the confidence interval. Okay. And then you're going to have at the bottom a row for the overall results. The diamond. Now some people here then, if up above it's a square, there's a diamond down here. There's various ways of doing this, but the basic idea should be the same. And so this is just where we started at the beginning. So you see this is just the rows with the labels. We've got the diamonds for the effect sizes, the confidence intervals, and the mean results. Bare bones, simple meta-analysis. Yes? Yes?
In some graphs you see the diamond is a bit wider and a bit fatter, or there's variation in
Yes.
the size of the diamond from one line
Yes.
to the next. Can you explain why?
Yeah. Sometimes they use the diamond, they make it the whole thing. So the diamond is both the confidence interval and the center. But the main thing that they're doing is they're often, for like this one that's small, they would try to make this diamond really big because this is getting more weight. And this one down here that has very little precision, they might make it small with a big line. So they try to have the amount of ink reflect how much weight it got. Now for me, that the width of that line tells me that. But their argument is that, but the line, it's opposite. The studies with these big lines, is this a very precise effect size or an imprecise effect size? Imprecise. So how much weight's it going to get? Not much. This one, precise or imprecise? Is it going to get a lot of weight or a little weight? A lot of weight. Now, which one gets more ink? Oops, the little one's getting, in this example, it gets less ink. And so that's what they're trying to correct is this conceptual, this visual problem that in this style, the effect sizes that essentially matter the most get the smallest amount of ink. So that's but a good question. I should have brought an example of one of those. Okay. Some comments on software. What software to use? You can use whatever software you want. You have several choices. You've got some specialized software like RevMan that was developed specifically for Cochrane. It makes nice reasonably nice forest plots. It's easy to create the forest plots. It calculates the effect sizes for you, but only for the basic situations. If you really have the means and the standard deviations and that sort of stuff, it can't handle all the wacky stuff that my effect size calculator can handle. And it does the basic analyses, but it doesn't do moderator analysis. Or at least, and somebody can correct me. I haven't used it in a long time, and they keep updating it. Does it handle moderate? No one? Okay. This is not the right class to ask that question to, probably. Comprehensive meta-analysis, and RevMan is free. Comprehensive meta-analysis you got to pay for. does a very nice job with calculating effect sizes, doing analyses. You code your studies right into it. It manages the bibliography. It's sort of the one-stop shop for meta-analysis, creates very nice forest plots, but it costs money. And when it comes to regression analysis, it can only handle one variable. The author, Michael Borenstein, he keeps telling me, yes, I'll fix that at some point. Eventually, he'll get around to having a regression program that can do a lot. Now, the other alternative is to use existing stats program, but sort of use add-on macros. Right? So Stata, there are lots of macros available for this. I've written some. Many other people have written macros. You download from the web, and now Stata can do meta-analysis. Right? SPSS, I think the only macros I'm aware of for SPSS are from my website, the ones that I've created. SAS, I've created macros. There's a book out that has macros, but I'm not aware of other stuff really on the web for SAS other than my stuff. R, anybody even heard of R? All right, a couple hands going up. Free program, really cool, kind of hard to learn. Lots of people have written meta-analysis routines for R, including a really nice forest plot procedure in R. Computing effect sizes, comprehensive meta-analysis does a very nice job. RevMan limited abilities, free on the web, not to plug my own stuff, but is my effect size calculator. Will Shadish also created one that's for sale, but it was developed about 12 years ago, and I don't know if it's been kept up to date. A few final comments. There was a lot. We jammed through a lot there. I'm proud of you guys. You made it. These methods continue to advance. I've sort of presented the bare bones, but in early July, I was in Ottawa, spending 3 days with a bunch of people talking about at a conference, the Society for Research Synthesis Methods, talking about these methods and having arguments about the advancement of these methods. There's a lot of active work in this area. Something that I haven't talked about, because it really should get an entire class of its own, is publication selection bias. How to assess for it, how to try to prevent it, etc. It's a very important topic and something I didn't want to shortchange with 1 minute or 2 minutes. The focus here was how to calculate those fundamental meta-analysis statistics. The other thing I told you, only one effect size gets to go to each prom. Well, there's some methods being developed that would allow for much more complicated relationships going to the prom. Ways of handling, essentially, just all the effect sizes all at once. Here you go, y'all can come. And actually, I think that talk is happening in the next room. It's pretty cutting-edge stuff, just been developed within the last year or so. Is quite interesting, but it won't be ready for just everyday use probably for a little while. And we're still kicking the tires to make sure it really behaves the way we think it is. Some common errors. Incorrectly computing effect sizes. Sort of the rest of this doesn't matter if you get those effect sizes wrong. And so you really want to make sure you understand what you're doing when it comes to calculating effect sizes. The other thing is a lot of people, they don't recognize data that could be used to calculate effect sizes. So often a lot of studies get kicked out that actually could make it into a study if they took a little more time thinking about how to calculate the effect sizes. Just using fixed effects models instead of random effects models. Remember, just use a random effects model. Not using moderator analysis to compare means. I talked about this earlier. A lot of people essentially just do a meta-analysis on subsets and look at which ones are statistically significant and which ones aren't. That's not the same as whether things are statistically different. And that's a very common error.